stromatolites and why did I come here? My name's Ben and my website's sciart.com.au. What I do is these artist residency projects where I work in ecology, geology and deep time history of natural systems. So I've done about 40 of them around Australia, interviewing a lot of scientists. So my kind of passion is getting into the deep time stories of landscapes. That's what really fascinates me. What this talk is about is to put the stromatolites into a context of deep time for you, to give you some kind of understanding of how deep time really is and how absolutely no one on the planet can really comprehend how deep time really is. Now, just for starters, just one example to start off with is that this is from the Hamelin Ranges stromatolite, right? 2,100 million years old.
Oh my goodness.
I know. Amazing. But this iron ore stromatolite here from the Pilbara, 2,700 million years old. Right? 600 million years between these two. Right? There's no evidence of eyes 600 million years ago in the fossil record. It's staggering, isn't it? And so if you cut through a stromatolite, you'll see there's these different layers upon layers upon layers. You could think of it as a microbial city. So you've got a layer of microbes that are photosynthesizing away, and then other sand grains come up, lay on them, and it's sticky, they get stuck to it, and then the microbes can move past them to get to the sunlight again, and then more sand grains come onto that, and so on, and they build up. It's approximated that the origin of the Earth is about 4.6 billion years ago.
Wow.
It's believed that life has its origin on this planet at about 4.2 billion years ago. Only 400 million years after the actual origin of the planet itself. That would have been a hell of a place to get started as an organic replicator. So one of the big questions is, where did it get started? The surface of the Earth would have been a bloody difficult place to make a living on. And I'm one of the people that strongly suspects that it was not the surface of the Earth where life got started. Somewhere deeper down in the planet. That could well be the origins of this particular tree of life that we're part of. There may well have been many trees of life getting started at the same time. But our tree of life is the only one we find evidence of. So I would imagine that just as the multicellulars eat the microbial, hence we don't find stromatolites all over the planet anymore at this time, so too our particular tree of life came to consume the others. Don't know. It's speculative, but it's an interesting thing to consider. So you've got this humongous amount of time, billions of years, but life gets going seemingly pretty quickly, and we call that LUCA. That's the last universal common ancestor. And if you think about what does that mean, that's where non-organic replicators become organic replicators, right? And then you can start to think about the gene streams, right? And that's a term that I coined after reading a book by Richard Dawkins, where he was talking about our bodies being banks of these rivers that flow through space and time. So think about a gene pool, the gene pools of the moment, right? And then you take the gene pool of the next generation and the next one and the next one and the next one and the next one, and you join them through time, through heredity, you end up with a stream. So the tree of life is the sum of these gene streams. And so if you think about it in that context, the mapping of the tree of life is a fascinating topic to try to understand where all these streams, all these species share common ancestry, and say you can plot them all the way back to the LUCA, the origin of all of that. And then you can think, well, there must be trees of life throughout the universe, and what do they all look like? But there was this one fella called Charles Darwin who, we heard, okay, he came up with this amazing idea of evolution and things, but he's not as well known for the fact that he's also the first human to actually attempt to draw the tree of life. The guy actually had the idea of, imagine if you could see all of life as one drawing, like in 4 dimensions connected through time, and it wasn't just imagine if, he then tried to draw it. He wrote, I think, next to it. And I think that's the most profound drawing of all time. How did he, I'm still amazed by that. At that time, and the thing is, if you compare his drawing with the knowledge that we have now, it's pretty close. So I found that absolutely astounding. It shows like the importance of things like voyages of discovery and exploring the world and natural history and the earth sciences and all these important things. One of the things that I do with the team that I work with is we make these large evolutionary tree sculptures. They're giant public artworks that you can walk inside of. We have Indigenous artists of the region's art on the outside. On the inside we have field naturalist art. And on the base plate you can see the shared ancestry of species.
Oh.
The journey that we all should be on is a journey of contributing to keeping the gene streams flowing. Gene streaming, the journey of renewal within the tree of life. And of course, if you're interested in your community having your own gene streaming sculpture, you can get in contact with me through the SciArt website. We do have one that is over in the east, so I'm going to start there because it's the youngest of the rocks, compared to west parts of Australia, which are much, much older. Have you heard of the Bunya Mountains, just northwest of Toowoomba? You've heard of them?
We live there.
Oh, really? Right, oh, fantastic. So have you seen my sculpture that's there?
Yes.
You have?
Yes.
You've seen the gene streaming sculpture?
Yes.
Right, oh, that's amazing. It's incredible. And if you noticed on that sculpture when you walk into it, if you look closely, you can see there's an arc that's running along the top of the whole thing. If you look at that arc closely, you'll see that it's got a little volcano on each one. It's got the dates of those volcanoes.
I'll have to look better next time.
Yeah, so that all connects together.
Yeah.
So at one point, you can tell from the volcanism of the Bunya Mountains, you can date it back to that hotspot, which is now somewhere under Bass Strait or something like that. So if you think about it in that context, you may be familiar that there's a range of extinct volcanoes up the east coast of Australia. In fact, there's several. The Cosgrove line marks them out. I mean, there's at least 3 lines of these volcanoes. Cosgrove is the longest of these lines. And if you go to a place like just north of Melbourne, Hanging Rock, that's the youngest of these volcanoes. But further north you go, these volcanoes get older and older. So if you can imagine Australia moving north, slowly drifting north, and it encounters this hotspot, and the hotspot starts to explode up these volcanoes. This hotspot, that's where you find them, is this magma chamber. And so it's moving along slowly, and that's how you end up with this sequence of volcanoes along the east coast of Australia. And if you understand the deep time history of an environment, you can also project into the future and get some understanding about what's going to happen in the future. And you can find that in other places of the world, say Hawaii, for example. That chain of islands formed by another hotspot. So we know that as Australia moves across and continues to go further north than this hotspot, it'll keep doing what it's doing, and it'll bring up other volcanoes, and so there'll be more islands. So after Tasmania, we'll end up with a whole sequence of islands after Tasmania from this hotspot. And they'll be populated with life and unique things like the Galapagos Islands or other places. So, you know, having an understanding of deep time past means you can project into the future in some capacity as well, which I find really fascinating. I'm from a place called Toowoomba in Queensland, which is a fair distance away from here. 20 million year volcano on the eastern side, 27 million year volcano on the western side. You go down the range and you jump like over 100 million years into a very different era of time. When you start to understand the geology of Australia, and anyone can do it on Google now, it's super simple. If you do a search for the structural geology of Australia, a map, so if you're travelling around, I highly recommend that you all do this. So you've got your map of Australia and you can see the different colours of the different ages of the rocks. So you'll be able to see how old the rocks are that you're on. And then ask Google, you know, what did Australia look like at the time when these rocks, you know? So it'll give you an insight into that, and then say, what did the plate tectonics look like this long ago when you see you're on these rocks of this certain age. So it'll give you sort of an insight into what the world looked like when, you know, these particular rocks were laid down that you're travelling over. And so that's what I love doing. That's what I've been doing for a long time. So when I mentioned Toowoomba, 100 million year jump there, but that's nothing when we compare it to something like the story of Uluru. Now Uluru takes us back to, say, a mark about 600 or so million years ago. The sediments of Uluru are certainly younger than that, but we're talking about this 600 million year mark because that's where we see the Petermann mountain ranges existing through Central Australia. And the Petermann mountain ranges are about the size of the Himalayas. If you can imagine what something like that would have been like. And Australia at this time is up much further north than it is today. And so as those sediments wash down from the Petermanns today, they're located in southwest of Uluru and Kata-Tjuta. So if you can imagine at the foot of the Petermann mountain ranges, a large alluvial belt of material, all these sediments wash down. We find the larger material, the larger boulders and bits and pieces, in a formation like Kata-Tjuta, which is actually larger than Uluru, and the lighter material is washed further out, and it builds up and up and up on the edge of a pre-Cambrian to Cambrian sea, the Ediacaran period and the Cambrian period. And that is what we find in Uluru. The boundary between the Ediacaran to the Cambrian is right there on the southwestern side of the sediments in Uluru, it's believed. And so if you can imagine India coming in and colliding with Australia, and that causes a lot of folding and buckling in Central Australia. And those layers of sediments building up and they get twisted up and around. So Uluru itself goes down something like maybe even 6 kilometres or something down under the ground and folds back up and around. It's absolutely extraordinary. And that's why we find the younger sediments facing the southwestern side. And the way we can think about that is the boundary between life-blind and life-sighted in the fossil record. Now, like so many things, as we discover more fossils, the age of different events occurring in paleo times goes back and back and back. But at present, the oldest evidence of an eye that we have is in a trilobite some 541 or so million years ago. Whereas 544 million years ago, there is no evidence of eyes. So what are the chances of that boundary between life-sighted and life-blind, as we understand it in the fossil record, being thrown up in this incredible formation that we call Uluru? You've got a better chance of winning the lotto than that actually occurring. And so the story of eyes in relation to Uluru might be that we might find even older eyes later. But luckily we've got quite a lot of the Ediacaran period in Uluru, so hopefully the marker point between life-sighted and life-blind will keep on getting pushed back, but stay within the Uluru sediments themselves. Because that's an incredible connection that you can make there. And when I think about early sight, I just shut my eyes and I put my hand across my eyes like that, and you can see that shadow that you get. That's an insight into what early eyesight would have actually been like. But it's an incredible advantage if you can do that compared to something that just walks around like this all the time. I mean, if you've got this going on, that's a massive advantage. I did a 4-month residency at Uluru and seeing it in the rain, and the frogs just go crazy. You would swear, like I'd been there a few days before, there was just silence, and then it's so loud you can hardly hear anything, when they really start going off.
It's fascinating.
It is, yeah.
Did you feel a presence when you were there?
Well, you do. You feel something.
I suspect it's got something to do with early experiences in the cot. Because when you're a baby, right, you've got these sheets are huge. The sheets are like, and I was like, big sheets, try to get over. And you forget that when you're an adult. But then you see Uluru, right? I was like, what is it about this thing? It's those bloody big sheets that I've got like almost no memory of when I was a baby. I have strong suspicions it's got something to do with bed sheets.
Pretty heavy sort of solid bed sheets.
Yeah, but it's got the same underlays. That's the story of Uluru, Central Australia. But it's nothing compared to wave rock. Go further west and we end up in 2.4 billion year old rocks, 2,400 million, and older as well, of course, much older. But that's like 4 times older than Uluru. And so that's when you're getting into the supercontinent cycle, this story of the supercontinents. Continent come together, break apart, come together, break apart. So we've got names for them like Nuna at 1.8 or something billion years ago, and Rodinia after that, and then Pangaea after that. That's the first of the supercontinents to be forested. And then beyond us, there's Amasia. That's one of them, or Pangaea Ultima, depending on which way you kind of think continents and that are kind of moving. It's not the end after Amasia either. There'll be another one after that as well. And so to put that into context, I'll stand up for this. You know, I like doing this. Do you like doing this?
Yeah.
It's good, isn't it? Yeah. And so this is the Cambrian boundary here, and this is where we are here, and this is the future of the Phanerozoic, and this is multicellular life here. And this is your deep time back to the Hadean, the origin of the Earth. So you've got this humongous amount of time of microbial life, and Luca, the last universal common ancestor, is about here. And then from here, you've got this second microbial age, and that'll go on and on and on. So the microbes will get their planet back and get on with doing things the way they used to do things. And why I say this will happen is because that the Earth will cool, we'll lose our magnetic fields. Plate tectonics obviously stops at that time. The atmosphere gets blown away, the oceans boil off into outer space, and then we end up with a Mars-like planet in the far future. And you know, it's obviously no one will be around to see that because eyes will well and truly have gone by that time. But we have a massive amount of time, more than we've already had, of multicellular life doing amazing things and throwing up this myriad of strange forms. This will just keep going and going for a very, very long time. So nothing to worry about in regards to that. So I've talked about wave rock in that context and that kind of porthole into deep time that opens up. But when you come here to a place like this, I mean, even this at 2,100, you know, there are stromatolites that are found for sure at 3,500 million years. And there's even speculative stromatolites at 3.7 billion years, you know. I mean, and all you need to do is walk on the beach here, and so you can look over, you can see the plants and the other things like that. You could access like our time, but remember I was talking about like jumping from one time zone to another, say with Toowoomba, we can do it all over the place. But when you stand on this beach and then you look out there at those microbial mats and you look at those stromatolites, you jump from our time to 3.7 billion year time. I mean, that is humongous, and you're not going to be able to do that anywhere else. So you also got to appreciate the sky, because they turned the sky from pink to blue. Billions of years of pumping out oxygen into the ocean, photosynthesizing, to eventually end up with the blue skies that we have today. So it's like the whole gamut when you come here and you go down onto those shells, and there's this theory that the idea is that a lot of those shells potentially were deposited from a tsunami. So what Phil Playford had in mind, that he found evidence of tsunami along west coast shoreline. He thinks that the shells are sort of part of that story, potentially. But you know, some of the stromatolites are huge, they're really big. And there is one idea that maybe that they're growing on giant boulders and stuff like that that were brought in from a tsunami. And hence that hill behind the caravan park there, you know, just when you're walking over, and all of the shells and all of that, it could have been an incredible thing to see that. But 10,000 years ago, if you come here 10,000 years ago, there's no Hamelin Pool. 12,000 years ago, you could go out to that giant canyon off Perth, which is larger than the Grand Canyon. You find indigenous people living in there. And so sea level rise, when sea levels rise, they don't necessarily just go up like that. They can bounce, like taking a basketball, throwing it on the ground. They can bounce pretty quickly when it happens. But here, sure enough, the water did come in. An incredible thing happened, that this seagrass started to spread over the mouth of Hamelin Pool. And I don't mean like lots of different individuals. I mean one individual. This is fascinating. This is one plant that has grown over the mouth of that Hamelin Pool and built up with the sand. And so the water just slowly flows in. So you get this incredibly salty, painful environment here for multicellular life. I found dolphins washed up and just dead stuff all over the place. There's a dead zone out there. But the wonderful thing is that there's no multicellular life to really speak of. Sure enough, there's little fish and stuff like that. But the snails and stuff that eat the microbial mats and things like that, they're not here. So microbial life can get on with doing what it used to do and what it will do and what it's always done here, and there's other places. I think it's the Bahamas and I think Thailand as well that does it. But there's not many places around the world where you can actually, and nothing at this scale. This is incredible. I mean, over there, somewhere over there, I was taken by a scientist, there's these things they're called sea stromatolites, and it's believed, the theory is that they're growing on the old sand dunes from the last ice age. These big, long dunes, and the stromatolites are going in huge, big, long lines, and they just go on and on and on, one line after the next after the next. If you go into the deeper parts of Hamelin Pool, you find, again, these humongous stromatolite things. It's saturated with them. So once multicellular life goes away, the stromatolites will just go for it, and they will create their own world. So although it's one of the youngest ecosystems in Australia, just over there, only 2,000-3,000 years old, it takes for that hypersaline thing to kind of really take hold. It is like the oldest ecosystem, that we know of as well. So it's the youngest and it's the oldest in that sense. But it will continue on for surely a long time to come. And that's why I love coming here. But if you look over at this mural, that is meant to be the Big Bang. That's the idea. And I have strong suspicions, as do many other people, and different papers have been written about this, that that singularity event, maybe we are living inside a black hole. That's an interesting kind of thought, and it is taken seriously. That's possible, and there may be universes that predate ours and after ours, and you can't dig around in the universe like you can dig around in the rocks on Earth. You can only sort of say, oh, well, could be. It's an interesting idea. But let's get on with this Earth story. So just imagine the beginning of the star, right? This star that we're orbiting, right? And there's this process called accretion. After there's tons of dust, and the dust goes into this, like a record or a CD, right? It gets like real thin. The dust is spinning around like that, and it's like little bits start to get bigger and bigger. They get bigger, and you've seen the rings of Saturn, right? You know how they're divided up, the rings? Well, it's because there's bits of rock and that moving through the rings like that. And they're like, like a bulldozer moving through and dividing up the ring bits and stuff, right? And maybe that was happening in the earlier stages of like planetary formation here. That's called accretion. So these planets, they start to become planets. They get bigger and bigger and bigger. Still, it becomes really crazy in the inner solar system. And you've got things like planets colliding with each other. You see this red hot world, this lava world, that's the Hadean. And how does the Earth come about to be as it starts on this journey towards where it is now? The first thing it has to do is to acquire a moon. And to acquire a moon, you need a planetary collision. At least that's the idea. Sure enough, moons and stuff can get captured, of course. But in this particular case, the theory that was put forward by Nardis and seems to have been substantiated with supercomputers, a planet the size of Mars, its name was there, colliding with the Earth 4.6 billion years ago. They smash together. Imagine what that would be like. And then this molten material starts to swing around this Earth, gets blown out, starts to swing around and starts to join together, and then you get this early moon. And it's going much faster than it is today. It's actually 10 times closer to the Earth, or even more than that, than it is today. So if you can imagine what a moon 10 times closer to the Earth looks like, and what that looks like when it rises over the horizon. You've seen moons rise over the horizon and stuff, right? Imagine something that's like that much bigger over the horizon, right? And you know it's coming because you could feel it because of the gravitational pull of the thing. And with the moon's, like it was cooling, right, with a thinner crust, right? But we've seen there's a moon called Io. It's close to Jupiter and it shoots off volcanism because of the gravitational pull. But is it possible, and this is an interesting idea that's happened, right, that the Earth's gravitational pull, the Earth pulling on that early moon, maybe does that cause volcanoes to come off the moon? And could you see them when you look up and the giant moon comes over? And with the early oceans, it would have been like a tsunami every day. And then the shadow of the Earth on the moon, because the moon's so much bigger, it wouldn't be like the eclipses and things that we have now. It would have been like a giant donut, temporarily you would see this big dark hole and this big glowing thing around it. I mean, it would have been really amazing and full on to be here. And so we don't have much evidence of the early continents and bits and pieces. Probably for good reason. They wouldn't last very long. It's a hell of a violent place. And so this goes on and on and on and on. As I said, I held up my arm before. Remember, I was saying, so somewhere in here, non-organic replicators become organic. So how do non-organic replicators become organic? And there was a paper that was published saying that RNA, which possibly is the precursor to DNA, seems to be forming spontaneously on volcanic glass, which is just massively confusing. But it seems, and also then there's these other things, like there seems to be strong evidence that under our feet down there is an ocean larger than the ocean that is out there, down there, right? There's more water potentially down there than there is over there. And so what does that mean? We've seen those deep sea smokers, the deep sea thermal vents and the smokers. So does that mean that little ocean down there, could be teeming with stuff down there, deep down, which is possibly, maybe more planets are kind of like that. Maybe life starting on planets is just it just happens on planets. Maybe it's just what the universe does. We don't know. But sure enough, the vast majority is microbial, and the multicellular stuff is a lot rarer, I think, would be a fair assumption. But if we move in, so you can see the stromatolites. So the stromatolites, well and truly, there's this period called, if you've heard of the banded iron formations up in the Pilbara, there's these layers of rock, red, white, red, white, red, white, and that is happening through this great oxygenation event that happens at about 2.4 or so billion years, where the stromatolites are in such numbers that they're pushing towards this side. They're trying to survive in their own waste product. They're emitting huge amounts of oxygen, which is poisonous to them. And so they build up in numbers and they just can't handle it. They poison themselves and they die off, and they grow in numbers again and they die off. But every time they're emitting these huge amounts of oxygen, it's emitting into iron-rich seas, dark green seas, right? And so it's pulling that iron out, so the rust and things you get. So, all the mining and stuff that takes place up in the Pilbara and other places, right? A lot of it is from the stromatolite action. So you don't just get blue skies, you get this industry as well, for mining and all these other things that are very important things that we do. And so if we keep going on, there's this period of time, this bracket of time called the Cryogenian, right? And it's sort of unclear why it happened, but what we do know is the whole world froze over, like a cue ball, in pool and that. You see those white balls? If you were on the moon and you look at the Earth, it would be like all white, the whole thing, and it maybe happened twice. And we know that because we find these drop stones in the Flinders Ranges, which is these round stones that get rounded out that way in Yongo. It only happens if they come out of a glacier, if they fall out of an iceberg. And I was doing a residency at a place called Shoalhaven, which is south of Sydney. You find all these drop stones, and these drop stones were like deposited through, and they were in sedimentary layers. They'd fallen out of icebergs and stuff, right? And so, but we know that Flinders Ranges at the time was at the equator. And so if there's icebergs and stuff at the equator, that means they're everywhere. And so it seems like this whole planet is covered in ice. And that goes on for millions and millions of years until it's emancipated by the volcanoes, because the volcanoes are pumping their way up through the ice and they're emitting these greenhouse gases. They warm the place up and eventually it emancipates the ice. So we have another extremophile event throughout the whole geological timescale with life. We get these extremophile events. So life is put under incredible pressure, but then out of that comes all sorts of strange things. Like we get animals. Right? Good question is, why are we made out of meat? And that's really moving into arty stuff, right? This is more on the arty side of the spectrum of what I'm saying. But it's a very valid question. I mean, we have more genetically in common with a mushroom than we do with a plant. If you do this, sure enough, it's a little bit more like a mushroom, And it does seem to be something to do with the utilization of electrical current. So our ancestral brethren that was departing from the fungal varieties of life seem to utilize electrical current to do other things, maybe to increase response time. I don't know, no idea, but animals do emerge out of this environment that we see, which is just a world covered in ice. And they're not like animals that we recognize. Some of them look like more like a leaf, and they have this foot thing, unusual things. Now we think of consciousness as the main game, don't we? We all like being conscious. It may not always be a happy experience, but it's something none of us really want to let go of. But what if consciousness is a byproduct of the coordinated response time to external stimuli? It's an interesting question to ponder. Although when it was happening, perhaps in the early Ediacaran, the recipients of this evolutionary asset were in no position to ponder such a thing at all. But throughout this process, heat-sensitive cells evolving into light-sensitive cells, and we get a process called encephalization. Encephalization means the evolution of a head. So how do you actually get one of those things? It's an important thing. We all agree with that. Very important. You talk out of it, see out of it, you eat with it, all sorts of things you can do with it. But before you could do anything with it, you have to get one. And to get one, you've got to do locomotion, which is actually you've got to travel through water, right? You've got to travel. So that means you end up with some front part, and that's the part that get more nutrients and stuff like that, right? And so you end up with mouth at the front, and the eye things start going to the front, and other things, all this sensory stuff. It ends up at the front. And I like the word a great deal, and I like what it's done for us. And then you end up with a rod down your back if you're chordata, and if you're another variety, you end up with an exoskeleton. But either way, this other thing that's going on is the evolution of a jaw. And with the evolution of a jaw, that's part of that predator-prey thing, and then you end up with the exoskeletons as protection against that. And we'll talk about the importance of these exoskeletons later for all sorts of things, including the fall of the sauropods. And probably I think what we'll end up finding is as we get more evidence of the Ediacaran, which is before that, the Phanerozoic will change. But if we move into this next bracket, we have that Cambrian period of time, and that's where we hear this question, what came first, the chicken or the egg? Well, the actual answer to that, of course, is the fish. If we go from the Cambrian times, when you think about the Cambrian, this is where we're seeing the foundations of Australia really are established by this time. But then beyond the Cambrian, we have the Ordovician. And you see that thing with the big shell, that squid thing, all right, cephalopod, right? That's an ornithocone. Now, ornithocones are about the size of semi-trailer trucks. If you can imagine what one of them looks like, the size of a semi-trailer truck. And this is a time before there was plants on land. But Australia was twisted 90 degrees counterclockwise at this time, and there was no east coast as such. Maybe where Broken Hill is, that's the edge of it. And there's this Larapinta Seaway that went through the centre of it. And whilst you had the Petermann mountain ranges, which I spoke of before, that formed Uluru, a parallel mountain range was rising up, and that's the McDonald Ranges. And it rises up through the Larapinta Seaway, and maybe there's an ornithocone that comes swimming through at that time. And so you'd have streams and stuff, of course, but that might be filled with kind of maybe more microbial life and things like that. And you can see that at a place like the Humps, which is near Wave Rock. If you go there, you can see these microbial rivers and things. But after the Ordovician, that's where we surely get the plants have established themselves on land in this Silurian time. And in the Silurian, we can think about how on earth did they actually get up onto the land. One of the theories is that maybe the plants came upstream, so they come from, in sea environments and stuff, and they come up these rivers, and then the rivers maybe dry out, as they do from time to time, and then the plants survive at the bottom of these rivers. So maybe when surviving at the bottom of the rivers, they dry out and think, oh, I can handle this, so there's boom, bust, and maybe that's one strategy you actually prepare to getting onto the land. Another way is through like a mangrove type thing. And we've found, sure enough, fossils of plants that look like they're root systems of mangroves. Not any leaves or anything like that. They're very, very different, but they look kind of like that. So that's in that Silurian time. And after the Silurian, we have the Devonian. And that's where we found evidence of mushrooms the size of almost as high as this roof. Not quite, but really big. And we thought they were like trunks of trees. And then you do a analysis of the stain and think, this is a mushroom. And so the largest things in the Devonian forest were these giant mushrooms. And in Windjana Gorge, if you're familiar with Windjana Gorge, Phil Playford, who figured out what the stromatolites are, he also did the mapping of the Windjana Gorge. And I got to meet him just outside here. And he said to me, he was 93 or something, and said, I've got cancer, I'm going to die soon. I'll tell you my life story. So we just pressed the record button. I sat there for 3 hours and he told me his whole life story. He's one of the most intelligent, amazing people I've ever met. It was so extraordinary. And so I highly recommend Windjana Gorge, and also to have figured out what the stromatolites were and what they did, and it's just staggering. So this Devonian world It has a mass extinction at the end of it. I didn't mention that there was also one at the end of the Ordovician, so it's the first and the second mass extinction. And then after this, that's where our ancestors come up onto land. So after this, we have the Carboniferous period. And the Carboniferous is where the forests are truly established, right? So they're pumping out a lot of oxygen into the atmosphere. And with so much oxygen, the arthropods breathe through their exoskeletons. So that allows them to get really big. For the first and only time that we're aware of, they actually got really big. The dragonflies were like the size of eagles, you know. The spiders were the size of your head. The millipedes were the size of cows. This is a huge world of insects and stuff like that. And because of the oxygen levels, it wasn't lightning as we understand it today. The sky would have just exploded. It would have been a very dangerous place to be in a storm during this Carboniferous bracket of time. And of course, it's where we get a lot of our fossil fuels from. And that terribly narcissistic question, if a tree falls in the forest and no one was around to hear it or see it, did it really fall? Well, you fill up your car with fossil fuels and there you can testify to the fact that it did indeed fall. So, you know, most of us travelled in cars and stuff to get here, right? So when you fill up your car with fuel, you might be filling it up with fuel from the Carboniferous period. And then in a couple of days later or whatever, maybe you're filling up with fuel from the Cretaceous period and other things. So you jump millions of years in time whenever you fill your car up with fuel. You're sourcing your fossil fuels from all over the fossil record all the time and you wouldn't even know it. But it is an important thing to be mindful of, that you've tapped into all these periods of geological time, or many of them, just by attaining locomotion beyond inseparalization. After the Carboniferous period, we have this Permian period. We've got Paleozoic, Mesozoic, and Cenozoic. This is ending the Paleozoic, that is early life, this early time of multicellular life. This is where we see incredible rise of the mammal-like reptiles and other things. There's so many incredible, like the Dimetrodon is one of my favourites. It's that reptile with a big sail on its back that you might have seen. So you can imagine them turning themselves to the sun. You know, the early synapsid gets the worm. But the thing about the end of this Permian period is that something terrible happened. A huge amount of lava got to the surface of the earth. I don't mean like a volcano. I mean like some people even speculate it might have even been the size of America. Now maybe not that big, but really big. You would have seen it from outer space. With something like that, you can imagine how that affects the planet. 95% of everything disappeared. I think it was more like 98% of everything disappeared in the oceans. And so it's hard to imagine what that would be like. It would have been absolutely hellish. The oceans turned pink through hydrogen sulfide emitting bacteria, so poison the ocean. Some death fog comes off the ocean and starts to spread across the land, choking stuff as well. And so that's not something that is common or happens often, and maybe it used to happen a lot back this time. I can imagine it would have been a common thing that happened back in the earlier Precambrian times with the thinner crust. We don't know how that actually occurred, but it certainly did occur, and you can find them up in Siberian traps. You can find all the evidence of that fog and stuff. That's just totally staggering. But good for us that it happened, because the mammal reptiles, some got through, becoming the mammals. And the other thing that got through was the thing that evolved into the dinosaurs, right? So that's the end of the Permian, that's the end of this Paleozoic, and now we're on to the Mesozoic, Triassic, Jurassic, and Cretaceous, dinosaur time. And in the Triassic period, that's where we see some really fascinating things happening. Some of these marine reptiles come into the ocean, right? And they become like ichthyosaurs. They look like dolphins, but they're some of them are like way bigger. And also these other ones become plesiosaurs. They come into the oceans later, and the plesiosaurs are the ones with the really long necks. And what's interesting is if you look at the world today, you can see how these mammals that went into the ocean, right? The ones that became like dolphin-like things, right? And then there's these other mammals that come into the oceans like later on, and they are this group, they become like seal-like things. If you look at photographs of seals under the water trying to catch fish in that, they're trying to stretch their necks. So, you know, it looks like I would take a bet that the seals are going to turn into longer and longer necked things I would not be surprised, because with the planet this size, the standard size, certain shapes, they're called morphologies, just keep throwing themselves up. They just keep reappearing. Like there's so many things that look like dogs, and I'll get onto our shape later on. So in the Jurassic times or thereabouts, some kind of shrew-like thing, a little thing that does this sort of thing, maybe it starts to spend more time up a tree. Certainly in the Cretaceous, it was up the tree. So in the Jurassic, we have dinosaurs such as Stegosaurus. The one with the spikes on the tail? Incredible animal. But to put that into the context of deep time, the distance between the Stegosaurs and Tyrannosaurus rex is greater than the distance in time between Tyrannosaurus rex and ourselves. The dinosaurs were around for a long time. But the interesting thing about the Jurassic, and I won't talk about it too long because we all know a fair bit about it, is that in the Jurassic, at the end of the Jurassic, you see a decline in sauropod numbers, the big sauropods, right? They were still around in the Cretaceous, but not nearly to the numbers that they were in the Jurassic. So what would cause all those sauropods to kind of start declining in numbers? One of the theories is that it's got something to do with the flowering plants, flowers, right? Because with the conifers and stuff like that, that's what they're used to eating. But with these flowering plants spreading through the forest, maybe the sauropods couldn't handle it. It was like, can't eat this stuff, because it would have been happening reasonably quickly. It seems to be happening, and it certainly takes off in the Cretaceous period in a big way. So, if not for the jaw, you wouldn't get an exoskeleton, because the exoskeleton is there to protect against being bitten and other things. And without the exoskeleton, you wouldn't get these creatures coming up onto land and evolving wings that become insects. Because it's like a Swiss Army knife, this exoskeleton. And so then you've got the wings, and then you've got insects flying through the forest. It sees some mutation on some plant, and it thinks, oh, it looks like me, I'll go and say hello to that. And it turns out that that is not an insect, they made a mistake. It turns out that that's the foundations, that's your first proto-flower. And the plant says, well, that was good for me, more of that. And so this mutational, however it happened, then becomes the foundations for the flowering plant world and stuff like that. But an interesting thing that's been happening all through this dinosaur time, and it started at that end of the Permian time, was that with the melting of the ice from all that hellish world I talked about before in the big extinction, all of that ice from around here in this part of the world had melted. So through all of the dinosaur time and all leading up to this time, that's 250 million years, the sun was shining on the highest points in the landscapes in the southwest. And that is why you get such incredible plant diversity in the southwest. They're called oakbills. Old, it's an acronym, the first letter of each one, like O, C, and so on, oakbill, right? So old, climatically buffeted, infertile landscape. That's why you've got so many weird plants here, because it's really old, 250 million years of plants evolving and not being interrupted on the high peaks. Climatically buffeted, because you've got seas to the west, and more recently, but still, many, many millions of years, 80 million years at least or more, you've got sea to the south. So you've got old, climatically buffeted, infertile, because it's like, granite, it's pretty tough stuff, and then it erodes away and becomes that sand, that fine quartz sand stuff. Infertile, you try growing and making a living in that stuff. Infertile landscape, so it pushes evolution to do strange things in strange places. And the southwest is certainly very, very strange. And then, of course, European settlers in their great wisdom decided to clear it all. But there's still a lot of it, bits and pieces of it left. And there are organisations that are trying to make sure that there's more reconnection with that material. And that's part of the reason I did that sculpture trial. I did was promoting an awareness of oakbills as opposed to the other, which is called a yodfell, which is a young, often disturbed and fertile landscape. That's where you get a lot of the farming and stuff like that. There's not nearly as many endangered species in yodfells as there are in oakbills. But it all dates back to that period of time just before the dinosaurs. So we move Triassic, Jurassic, and into Cretaceous. Now in the Triassic, we have that breakup of Pangaea. If you've heard of Pangaea, the supercontinent, it sort of looked like this sort of shape. Australia's over here. It comes up and it breaks into two, but then through Jurassic and into the Cretaceous, all of Gondwana is breaking up. What would cause a giant continent like Gondwana to break up and head off in different directions? That is a very good question. What did that? Was it another magma plume that couldn't get to the surface? Or was it another asteroid impact event? What did that? It's not really clear yet, but it certainly did it. And with all of that volcanism, because we've never experienced anything like it, what would it be like with that amount of volcanism? So yeah, it got hotter again, you know, and the sea levels rose again. And one of the things that I like thinking about is the Eromanga Sea in Central Australia. This guy called Sturt, he dragged that boat out. I was the artist for the Birkenwells Environmental Expedition in 2010. And we went out and we saw Sturt's boat out at Tibooburra. And you know, the funny joke is that he missed the inland. Sure enough, there was one there, but he missed it by over like 80 million years or something like that, but he was right. There was a sea there. Yeah, just missed it by a bit. And you could see all of the round stones and stuff that were like shaped by the inland sea and stuff out there. It was like this riddle of why there's so many big round stones along there. So that edge of that seaway. But when I was out that way, I was with a geologist, and he said we're about to go into the bottom of the Eromanga Sea. So we're going down this thing that looked like a hill, but it was actually said this is a beach. And then we hit the bottom of the sea. We're driving along, and he said, "See over there?" And he said, "There's a whole bunch of flat top mountains, these mesas, and what it is the sediments that go to the bottom of a river. They get harder and harder over time, right? They become the most resistant material in a landscape once that river is dried up to erosion. So the whole landscape erodes around it. That bottom of that river becomes the top of the mountain. So when you join the mesas together, you can join the dots and you can see where the old paleo channels were. So one aspect of a former landscape begets some extreme feature of a present landscape. So landscapes beget landscapes, and this story continues. And so logic can help you understand and peel back these layers of lack of understanding about the world. So to drive along the bottom of the sea, seeing the Chronosaurus, seeing the plesiosaurs, it was seeing, the Chronosaurus was like a pliosaur. It's like a gigantic crocodile creature, like full-on beast. And I think the saltwater crocodiles, that's where they're heading. I have a strong suspicion that saltwater crocs are going to fill that niche again. They're going to get really big, and they'll become serious out in the oceans in the future. I have no doubt about that. So flight's happened a number of times on the planet. First time we have the arthropods taking flight, and that might have happened the Devonian period. I'd say that they're probably there. In the Carboniferous, they certainly are. But that's the first flight. And then after that, we have the pterosaurs. We find the early pterosaurs in the Triassic period. So they're not dinosaurs, they're flying reptiles. But by the end of the Mesozoic, there are pterosaurs that are the size of small planes. Quetzalcoatlus is one of them. And I've seen some of the fossils of that. And so they flew with their little finger. And the little finger of a Quetzalcoatlus, you could see my arm. I mean, the bone is like that kind of size. It's huge. These little fingers. And they were the size of a giraffe. So how does something like that get off the ground? They were trying to imagine how it would do it with guys walking around with crutches, launching yourself off your crutches and up into the air. And then we have that line of dinosaurs that takes flight and becomes the birds. They seem to be doing it with their middle finger, which of course is what they gave the asteroid when it collided with the Earth, because the birds went on. No idea how they survived that thing, but they did. And we get that iridium layer around the Earth. It ends the age of the dinosaurs, but maybe there wasn't one. We found evidence off the west coast of Africa of a second asteroid impact crater at the same time, or very close to. So can you imagine what that would have been like? Two of them. The second one's not as large, not nearly as large, but it's still a huge, huge event. And of course, it's a rare thing for asteroids to hit the Earth, so two of them just happening to hit at the same time, the odds against that are astronomical, quite literally. And so quite possibly maybe it broke apart. Maybe it was travelling in broken up bits, but it looks like it may well have arrived pretty much at the same time. It's looking likely that that's the case. You can never say with certainty, but what might have happened is instead of one giant tsunami like spreading across the planet, maybe you'd have the force of the two, maybe two waves of this incredible material thrown up from both of those asteroid impact craters meeting at some point. I mean, it's amazing that the mammals survived at all. It's just incredible. And the birds. Don't know how they did it. And the fish and other things. Fish, it makes a bit more sense, but yeah, it is hard to envisage, if you can, what that would have been like. I mean, the force of that's more than all of the nuclear weapons that we've got exploding at the same time. But it's by no means the end of the story. That ends the Mesozoic middle life. But there's a Cenozoic time up here. And then we move into all this mammal stuff, right? The interesting thing is that because there's no giant dinosaurs walking through the forest, smashing stuff up, the forests get really thick. When they get really thick, you get a lot of shade. And so the plants invest more in providing nutrients to their seed. And we call that fruit. And then the mammals that are around start to think this stuff tastes good. You know, and so if it wasn't for the asteroid that knocked off the dinosaurs, we may not have fruit in the abundance that we have it today. The much deeper shaded forests of the time. 55 million years ago, 10 million years, only 10 million years after the dinosaurs die out, you've got like a forest in Germany, which is this rich tropical kind of forest thing. There are no rainforests in Germany now as such, but there were back then. There was little horses that were running around, like little things. There was giant birds that would eat them. And there was like an ambush predator that would throw itself out of the water like the crocodile, very dangerous animal. It's called ambulocetus. And ambulocetus means walking whale. Right? It's the foundations for the whale lineage. There's a bone in its ear. You only find it in whales. You don't find it in other stuff. And there's primates there. So based on where we find those primate fossils 55 million years ago, although we say, yes, we're all Africans, we could, if we follow that gene stream back, think of ourselves as Europeans, and to get more specific, Germans. Which is interesting because it was only 20 million years ago or so that Africa came up and formed that land bridge so that stuff could walk into Africa, because remember it's a Gondwanan continent, right? So the primates walked in to Africa, and somehow they hitched a ride, this is the idea, most people think it's right, on bits of branches and stuff, and ended up over in Madagascar. That's the lemurs, the old world monkeys. So the primates were like a feral species in Africa, and that, just like the feral cats are today in a different kind of way. I don't know what craziness they would have done, but they would have had a major impact at that time when Africa collided in. If they'd come in, they'd spread like feral cats across the whole of Africa, moving into tons of niches, clearly, because there's just so many different types. They have a long time there. You know, so the question is, what comes first, the hand or the foot? Do you know which comes first? Hands or feet? You don't have feet on your hands, do you? The hands come first. So the idea is you're a shrew-like thing, and you go up the tree and you live up there in the Cretaceous times, and then you get this kind of stuff happening. And sure enough, if you don't have this, then you didn't go up a tree in your ancestry. This does trees, all right? This is the tree thing. Right? So another idea is that Australia breaks away. It's the last of the Gondwanan continents to break away. And as it moves north, maybe it affected the climate, no doubt, in Africa. And maybe it helped to dry it out. There's always multiple factors. And so I'm not just saying it's just the one, but it might have had something to do with that. So with Africa drying out, then you've got the primate things spending more time down in the savannas and stuff like that. And that's why I said which comes first, the hand or the foot. So this thing goes up to the front, becomes this thing that you can run away from the giant cats with, and sort of look up and look around and stuff like that. So there's more of that going on. You know, sure, some kind of foundation foot was there. I'm not saying just all turn from hand to foot. I'm just saying we got a better foot for running around in those savannas at that time as it dried out. So when we move through this massive bracket of time, I won't go into all of these different creatures from this, you know, that's a mighty bracket of time there from the end of the dinosaurs, some 65 or so million years ago to the present day. But we'll jump quite a bit of that because there's a lot of interesting things. It's like, even in more recent times, there's like 14 ice ages. So again, extremophiles, right? the stuff like the Toba explosion. But I'll come to the story when we actually eventually the things that became us in Africa left. Hominids have left a number of times, but when the Homo sapiens walked out of Africa, some of them went up north and they became bleached Africans. And you become a bleached African for lack of vitamin D because it's an ice age environment, right? Dark sky. And if you're a dark person with a dark sky, you won't be getting the vitamin D that you need because you've evolved to block that because you come from Africa. So you become a bleached African, you can become white over time. It's healthy if you're in that horrible, dark, cold environment. We do have some sense of global dimming today. All the planes flying around the planet. Apparently after September 11th, the planes were obviously grounded and it become a lot hotter in New York. No dimming, you see. But the interesting thing about that world is it had all the domesticatable animals and plants in it apart from the llama, which is a disagreeable domesticatable animal. And so all the foundations for civilization are there. So you can do things like you can farm, you can do crops, you can have time to allocate people to building houses. You can start to talk about monotheistic ideas and all these sorts of things. And you can do all of those foundational things that lead to civilization, right, as we understand it today. But if you're an African that heads off and ends up in a place like Australia, it's a very different story. You don't have any domesticatable animals, you don't have any domesticatable plants as such, maybe a little bit, but not a great deal. Nothing like what the Africans got that ended up in Europe. But what you do get is you get some other treats. You get like megalania, and that thing that's above the crocodile there, that megalania, that's a 6 metre long goanna. So something like the Komodo dragon that you've seen, that's actually a shrunken version of megalania. So it's believed that these things come from Australia and they walk out during one of these ice ages, and then the sea level rise, they get trapped on that island and they become little ones, right? But I've seen a reconstruction of megalania, and that is no joke. That will run you down and eat you. And so it disappears fairly quickly when humans arrive, because it seems like I would take a guess that we probably just traced them, found their nests, cracked their eggs. That's what you would do to get rid of that monster. Wanabe were there as well. That's that python over there. And I met the guy that found Wanabe. He was in a quarry near Narracor Caves. Just put his hand through his next chamber and pulled out this like a giant vertebra. And the idea is this is a huge python, but maybe that's the foundations for the rainbow serpent there. And then he also had at his house, which he should not have had, he had a Thylacoleo skull. And that's a marsupial lion with like Nosferatu fangs, flat face, it's got hands. And when they found it, it just had a thumb sticking up like that. And I went to where they found it, it was just a thumb. And there's a big claw on it. Clearly it's been up a tree. And all its back teeth, it looks like they're fused together, but they're not. It's just bone. And they did a study on its bite force. I think, Christ, this thing's biting harder than a lion. So it maybe is the origins of the bunyip or something, you know. And Australia's first drop there, of course. It would jump onto the diprotodons and other things like that, which are the big, shaggy kind of wombat things. Giant wombats were there, but the diprotodons are like kind of strange, kind of hippo-looking shape. Very unusual and a great loss to the Australian meat industry. I really mean that, because the soft feet. We take these cows and these hoof things all around the place and they compress the soil and they blow it away. So it's a shame to lose them. The platypus is there obviously, but actually when you talk about biogeography, it's the movement of these clades around the planet and species. There's a fossil of a platypus that's found in South America and it's got teeth. In more recent times, comparable to other things, you could see the movement of these marsupials. And the professor that gave me that information said the marsupials, they seem to start in China. And they move across and then into the Americas and go through North America, South America, across Antarctica, into Australia. That's how they got here. That's the biogeography of things, you know. So think about that every time you have a sandwich. Where do your different ingredients come from? They come from all over the planet, you know. So that's the world that the indigenous people of Australia walked into. The worlds have changed again and again and again. And the shoreline was extremely different. It's part of this thing called the whole. that you could literally have walked in through Papua New Guinea. Maybe it was a little bit marshy and stuff, but you could have walked in. And now we're in this world, of course, and if it was not for the stromatolites, none of that happens. None of this happens. Something else happens. You know, it'd be a good question if you ever meet an alien. One of the first things you'd want to know is, are you water-based life form? If not, you're something else. You know, do we just do water-based life in the scaffolding of this universe, or is it possible to do silicon as well? That's a good question. But what we do know is that beyond this point, we are heading towards either China, it looks like. So one of the jokes there is that we're going to be doing a home delivery of our natural resources to China. And I got an inflatable globe, one of those ones from a $2 shop. This was a highly scientific experiment. And I coloured in with my good colleague and friend Ben Price, Gawler and the Pilbara and the Yilgarn. These are the oldest of the rocks of Australia. And we followed them back in 50 million year intervals. When you trace them back, you can see that Australia's been all over the planet. So every 50 million years, we coloured it in again and again and again. And over time, it took us 3 days and a few bottles of Merlot, but we got there. And we, so it goes down and up and down and up. Australia ends up going up over the northern hemisphere and then heads down and goes up and around in South America. And the oldest part of it was 3,750 million years ago, was the last evidence of the Pilbara where China is now. So we're also made in China. The other theory is that we miss China entirely when we're going north and we end up, as the Beach Boys advocated, and we go to Hawaii. So that's the other possibility as well. And India's already done it. It's showing us our future, something like that. And I've no doubts that wherever the mountains are, if they're in Southeast Asia or if they're over in the west coast of America, the descendant of the feral cat will be there. And that's a fair way into the future, and one of the words for that is Amasia. It's actually got a name. There's even an idea that South America will swing around and collide with the south coast of Australia, so there could be even more mountains there. And that's just part of that kind of upwelling story when you think about it in that regard. I'm often asked about global warming. I mean, what does it mean? Yes, it's natural. But in recent times, there's been something like 14 ice ages. Glacial into glacial, glacial into glacial. We should be going into another glacial period relatively soon. I mean, maybe it should be happening already, but obviously we're not. You see, what we've done is we've dug through deep time and started to burn the paleo dead from hundreds of millions of years ago. The ancient Carboniferous forests. Burning them and putting them up into the atmosphere as we've done. We know about landfill. Well, we've also got skyfill in our time. We've filled the atmosphere full of greenhouse gases. We've behaved as if you were to dig down into our time and look at the chemistry of our time, you'd think, wow, there must have been a lot of volcanism at that particular time because of all the greenhouse gases. But what happens with a lot of volcanism is that initially you get the volcanoes. That also ejects a lot of ash into the atmosphere, and you get global dimming if it's happening at a large enough scale. It cools the planet for a time. It can even send the planet into a mini ice age. The volcanoes can be that powerful. And then after that, with all the greenhouse gases also emitted from the volcano, that's where you get global warming. But throughout the whole geological time scale, since life started to really happen, particularly on the land, what you do see is a whole sequence of these methane spikes where large amounts of methane are emitted. That happens when the planet destabilizes. Maybe there is a lot of volcanism and the planet heats up to a point, and then you get things like permafrost starting to melt, and that's emitting large amounts of methane. You get the oceans warming, and that's starting to emit a lot of methane, because the methane is a natural process. It builds up over time. Rivers that flow out from giant forests, bringing all this detritus out with them. The colder oceans, they keep that methane deposited down in the bottom of the oceans. And the permafrost that we have up in the northern hemisphere, that houses huge amounts of methane. I've heard it's something like 5 degrees of global warming is locked up in that methane. So the most important thing is that we don't destabilize the planet to a point in which the planet will just get into another runaway greenhouse gas extinction event. That's the threat. We might destabilize the planet to a point where it will move into another world, another way of being. And that'll be great for things like the crocodiles. The crocodiles at the moment, the salties, you could find them way out to sea. And if the sea levels rise again, sure enough, maybe the sea will come in through the Gulf as it did previously. It might happen again with enough sea level rise. So you won't just have the shorelines remapping themselves fairly drastically. You could also have another inland sea. I can imagine the future with the saltwater crocodiles giving rise to another kind of chronosaur or Queenslandicus type creature that we found in the Cretaceous Sea in inland Australia. Down at Cooperpedy, you might have saltwater crocs swimming around. Don't know. It's fascinating. But it will cause a massive amount of displacement, and not just in the Australian population. Obviously, there's 1 billion people to the north of us in Southeast Asia that their homes are going to go underwater. They're going to come here. And who could blame them? So that's why it's very important to be mindful of the sensitivities of the biosphere and the importance of maintaining the status quo, sustainability. But if you're interested in our kind of life, continuing in this way, just don't destabilise the permafrost in the Northern Hemisphere. It's the destabilising of moving into, releasing like 5 degrees of global warming and methane and stuff like that. That's the real game changer. Opening up the gates to another saurian age, potentially. And I guess what I mean by that is that the birds have in their DNA the capacity to grow fangs. You take a chicken and you turn on that DNA that grows teeth, and you got a nice long line of fangs. The theropods are still here, and that's that group of dinosaurs that also include Tyrannosaurus rex. Now, I'm not saying that birds are the descendants of Tyrannosaurus rex. It's a different lineage. But they're closely aligned with raptors. And although the sauropods are gone, they are not coming back. We could well give rise to a second saurian age. And in that second saurian age, I guess a good place to be if you were a rodent would be up a tree or in a burrow. And that's what happened during the time of the dinosaurs. In Cretaceous times, it's believed that our ancestors might have been shrew-like creatures living up trees. So why wouldn't the rodents go up the trees again? And if they go up the trees again, then eventually they'll start to get hand-like things. They'll start to do kind of higher mathematics in the head, comparable to living on the ground and running through the grass. If you're up a tree, you've got to calculate all those distances between the branches and all that kind of stuff. That's complicated. And these rodents of the future, they might live in families up trees. They might sit up in their tree and they might look out at all of those leaves glistening in the sunlight. How nice it is, sunlight through the trees. Photosynthesis we beautify. That could well be the origin of flag flying. If you're some primate in your tree, this is my home tree, here we do things this way, and I'm proud of this place, and these leaves, they make me feel relaxed and proud, and I'm happy to be here. Now, there's some kind of correlation between getting a big pole and putting a big coloured piece of cloth on it and watching it flap around in the breeze and thinking, here is my nation state, here is the embodiment of something that I believe in. So flag flying has its origins in those forests with the primates sitting up there thinking, this is my place. And as time goes on, if indeed there is another inland sea in Australia, that sea is doomed, because Australia, as it goes north, we get another mountain range rising up into the far future. What I am reasonably confident of is that in those mountains, wherever they may be, we might have mountains to the north of us. We might even have mountains to the south of us, if indeed South America does swing around, as some people are proposing, and collides in with part of the south coast of Australia, so 2 giant mountain ranges. you may well find up in those mountains the descendants of the feral cat. Big, shaggy, giant, white, lion-looking things. And if one of these cities is lifted up, say Melbourne's one potential contender for this, if there is another mountain range that comes up through there, and maybe it erodes out of the side of some giant mountain range, these bits and pieces of Melbourne in the future, and plastic bags and stuff flying out of these things across these bizarre tropical forests in the far north, bouncing down along some future beach millions of years, bits of plastic floating out into the future oceans. The Earth will never forget us, and the sediments of our time will be released, and due to the lack of biodegradability of this stuff, end up being deposited in future brackets of time as well, in the sediments of their time. So we certainly could think of ourselves as the fossils of the future. And in that far future, no doubt there'll be some places that become super saline and the rest of it, and then there are the stromatolites doing it again. And so there's many reasons that you could think of the living end of the tree of life. That is to say that through heredity, and if you connect one generation to the next, to the next, and the next, through this process of gene streaming, that's the process of renewal within the tree of life, it's sort of reasonable, instead of talking about it as a tree, to talk about it as a stromatolite, the stromatolite of life. You can see the layers of the generations striving for the sunlight. You can imagine those large deltas running down from that mountain range in the future. The future of Australia is potentially tropical. Uluru might end up as an island for a time. Don't know. Uluru might end up with a forest around it in the future. It's amazing and it's dynamic and it keeps changing. But in the far future, some kind of rodent does go through that process again, and anything that gets smart is going to be invested a long time up a tree to get the foundation calculated, mathematics stuff in the head, and the body plan that can create a feedback loop with the world to just get smarter on things. But if it does do that, it will dig down to our time and it will find a couple of things. Firstly, it will find this proliferation of the right angle in middle-sized world. Because there's these creatures that that's what we do, we make right angles, we just spread them all over the place, right? Now, obviously these days most of us live in cities, and I don't think it's a coincidence that possibly the most popular religious symbol that we have is literally an accretion of right angles, because cities are full of them. And if they dig down their hidden museum, then it gets worse. Because then they'll have dug into a thing where they'll see dinosaurs, and they'll see all these creatures that I spoke about all together, and they'll think we live with all of them. You know, it makes perfect sense. And then there'll be illustrated books of us living with the dinosaurs and all the rest of it, you know. And so falsifiable science can produce definitely the wrong answers, and it'll totally disprove whatever they call it. They won't call it Darwinian evolution, they'll call it whatever Zordak evolution or whoever comes up with it, you know. But because we've spread everything everywhere, right? We just move ships and planes around, and so here you go, and weeds and ferals all over the place. So it totally mucks up evolution. But it's been approximated that it takes, in fuzzy numbers, about 250 million years or so for our star to orbit the center of the galaxy, that supermassive black hole. And interestingly, our star is moving faster, it's believed, than those arms of the Milky Way galaxy. You've seen those spiral arms. And so we do at times like move through them. There's some speculation about whether or not or how that actually affects things on this planet. Our home star is orbiting the galaxy, and the planets are orbiting the star. As they move with the star, they orbit it. Can you imagine it? Can you see them? The helixes that they're forming? The planets are all creating their own helixes as they move with our star around the center of the galaxy. But of course, we're not coming back to the same place, because galaxies moving at an incredible speed through the universe, and we created a calculator for that. How far have you traveled through the universe since you were born? That's the speed at which the Earth's spinning on its axis, the speed at which the Earth's orbiting the star, the speed at which the star's orbiting the centre of the galaxy, the speed at which the galaxy's moving. So if you say, okay, everyone's born at midnight, and then you can calculate those 4 factors, and you can end up with how far you've travelled through the universe since you were born. It's an impossible number. But then far beyond that, we have the collision of the Andromeda galaxy and the Milky Way galaxy, and so that'll be amazing. We end up with a giant elliptical galaxy, and then if we go beyond all of that, we won't be here by that time, but if life will still be happening throughout the universe. And the last thing I have to say is we do live in an interesting time, which through falsifiable evidence-based reasoning and the rest of it, we can verify that we do live in an interesting time. And what I mean by that is that in the far future, the galaxies will move so far away from each other we won't be able to see them, right? And that we won't have any evidence of the microwave background radiation from the Big Bang. You won't be able to hear it. And so you might end up with a civilization that's as powerful as Star Trek or maybe even Star Wars, but it'll look out into the universe. You'll come up with an understanding of the universe that there's just one galaxy, their galaxy, alone in the void. There's no Big Bang, there's no nothing, there's no multiverse. That's it. It's just them. So it'll give you totally the wrong answer. And what of the far, far up when eventually all the stars are going to go out? It'll be cold and dark and full of black holes and planets and bits and pieces that escape the destruction of their stars. So perhaps the multiverse, if there is such a thing, is full of these graveyard universes, all potentially with their own scaffolding, their own framework for being. But it will have had an incredible journey. So it all depends on how far down the rabbit hole you want to go, how far down the bilby hole you want to go, and really how far down the wormhole you want to go. And if you did go down that wormhole into a black hole, you may well be the seed for another universe. If the black holes are giving rise to other universes, and who knows? Don't know. It's a nice thought. And in those places, some of them are suitable for life. Could be like froth, if you think of it that way. Next time you have a bubble bath, pick up a bunch of those bubbles and have a look at them. Maybe our universe is just one of them. But I don't think it's really like that. The journey that we all should be on is a journey of contributing to keeping the gene streams flowing. Gene streaming. The journey of renewal within the tree of life. And of course, if you're interested in your community having your own gene streaming sculpture, you can get in contact with me through the SciArt website. Thank you very much.
Well, why hasn't that turned to dust yet?
Don't know. You know, things fossilize in different environments in different ways. So under certain circumstances, under certain conditions, like if you were living in like the desert, right, in Pangaean times, in a Triassic desert, right, we can't find any evidence, hardly anything from the deserts of those times. But in areas where you've got wetter environments, you know, you find a lot more kind of fossils in like wetter environments and stuff like that. So along shorelines is a good place. If you're planning on fossilizing yourself, that's a good place, or to die in some riverbank or something like that.
I remember that.
Yeah. I've even got the recipe for it. I consulted with paleontologists about it. I have the secret formula for fossilization. But if it wasn't for the stromatolites, you know, I wouldn't be here talking about this. We're talking about all this amazing stuff, because it just would have stayed as some rock planet, sort of like Mars, right? So if not for this, we have Mars here. That's it. That's why they're so important. That's why I love coming here. They're cool. So that's about it. Any questions?
That was pretty amazing.
That's a good recipe. I like it. Isn't it? Where is it? Yeah, Hamersley Ranges. 2,000 100 million years ago.
So you put it in your